In this video, we will be talking about indeterminate forms and how to apply L'Hopital's rule. In this first part, we see that we do have some algebraic things that we can do with our limits. Something for us to keep in mind that we did discuss in class today, just because our algebra rules work nice and neat, that doesn't always apply whenever we're looking at some calculus problems. Whenever we have an indeterminate form, then we're not real sure about here these values. We don't really know what's going on. We really have some things that we need to look at. In these first few examples, it's going to serve to remind us of our algebra techniques. When we plugged in, we had 0 over 0. And we always said that this might be a good place for us to factor and then cancel. And that's what we need to do here because we do have a point of discontinuity. So if we look at our limit as x approaches 3 of our factored form, so the numerator is prime, but the denominator, we can factor this. And so we cancel here, and hopefully we see that we do get 1/6. And that's a good algebra review. Now looking over at part B, here we had x is approaching infinity, and that is talking about a horizontal asymptote. And here we talk about the power struggle, and we really are looking at our dominant powers, and we look at that ratio of negative 5x cubed over x cubed, and we see after that power struggle we end up with negative 5. And so that limit is negative 5. The horizontal asymptote for us to remember is y equals negative 5. A good thing for us to remember is all these different methods that we do have for solving limits. And again, usually if we can go to a graph approach, that's a little bit easier than some of the others. But it's always a good thing to look for. And then with L'Hopital's rule, notice that if we're talking about a, which is what the limit is approaching, is any real number infinity or negative infinity, then we have all of these different rules going on. And notice all of this does fall under L'Hopital's rule. So notice here we're looking at 0 over 0 or plus or minus infinity over plus or minus infinity. Those conditions must be met. And then we have an indeterminate form, and then we may do L'Hopital's rule. So very important for us to remember these concepts here. So again, especially this one, when a limit gives a value of a over 0, then the limit's just not going to exist. We have a number over 0. However, when a limit gives a value of 0 over 0 or infinity over infinity, then the limit is called indeterminate form, and it may or may not exist. Then it tells you L'Hopital's rule may be applied. So let's see if we can keep in mind we're looking at these forms here. That's important. Okay, so here, an important tip when demonstrating that L'Hopital's rule applies, write the limits of the numerator and denominator separately. Remember that the limit of a ratio only equals the ratio of the limits of a numerator and denominator, provided that the limits both exist and that the limit of the denominator does not equal 0. So again, that's something we're looking at here. So we do need to look at the limits of the numerator and denominator separately. And when we do that, notice here we have the limit as x approaches 1 of natural log of x, and that's going to give us a 0. And then we have the limit as x approaches 1 of x minus 1, that also gives us 0. So now we are looking at 0 over 0 situation, and so now we can apply L'Hopital's rule, and L'Hopital's rule is telling us that we can do the derivative of the top and bottom and look at that ratio, and the derivative of the natural log of x is going to be 1 over x over, and the derivative of x minus 1, that's just going to be 1, and so we see this limit does end up giving us 1. Okay, for example 3, and again looking at this, just doing some mental math, it looks like we are going to get 0 over 0. But it's always a good thing here to go ahead and write it out. So we're going to look at the limit as x approaches 0 of cosine of x plus 3x minus 1. If we substitute in here, that's going to give us that's going to give us positive 1. Goodness, I was thinking of pi. Plus 0 minus 1, so that does yield 0. And then if we look at the limit as x approaches 0 of 4x, that is also going to give us 0. And so here we can again do L'Hopital's rule. And when we do that, we're going to look at our derivatives. So we're going to say L'Hopital's rule here. And we are going to have the limit as x approaches 0 of the derivative of cosine of x. That's going to be negative sine x. Derivative of 3x is 3. Derivative of minus 1 is 0. All over derivative of 4x is 4. And we can now plug in our 0, and it looks like we're going to end up with 3/4. Okay, for our next problem, notice that x is now approaching infinity. And if we were to look at each individual part of this, we're going to see that the limit as x approaches infinity of e to the x, that's going to give us e to a really big number. And so we're going to say that that is approaching infinity for sure. And then the bottom part, we have the limit as x is approaching infinity of x squared. And again, that's going to be a really big number, and then you're going to square it, so that is also approaching infinity. So we now have L'Hopital's rule where we would have infinity over infinity. And so we now have L'Hopital's rule that we can set up. And so we are going to have the derivative of e to the x. X approaches infinity is going to be e to the x over 2x. And here we can see from this that we are really approaching infinity with this, because e to the x is going to be growing at a much faster rate than 2x. So we can go through L'Hopital's rule again, or by reasoning we can say that this is going to approach infinity, or some people say does not exist. Either one would work. All right, number 5, with this one, again, going through the same process, it's a good idea to look at individual limits here. So the limit of the numerator as x approaches infinity, that's going to give us 4x plus 1 over e to the x. So that looks like that's going to be shooting off toward infinity. And then the limit as x approaches infinity of 3x, that again is going to be going toward infinity. If you're not sure about that, over to the side, like a little sidebar thoughts here, is you can look at this as 4 times really big plus 1 over really big. And so that's the idea that I'm looking at here. So this is going to be really huge. That's going to go out to 0. So that's why we're saying infinity. And by that same idea, that's what's going on here. So we are going to apply L'Hopital's rule. And so we have to be careful when we do the derivative there. We do have the limit as x approaches infinity. The derivative of 4x is 4, and then here the derivative of e to the negative x, that is still going to be e to the negative x times the derivative of negative x, which is negative 1, and then that's going to be over the derivative of 3x is 3, and it's a little bit easier to tell what's going on here if we go through and rewrite this. So we see that we have the limit as x approaches infinity of 4 plus negative 1 over e to the x, or you could say minus 1 over e to the x, and then that's all over 3. And so again, that's going to be heading toward a 0, and so our limit is going to be 4/3. All right, moving on to our next problem. Again, very similar idea here. We are going to be looking at pi, and again, let's plug the in and see what happens. We have the limit as x approaches pi of sine of pi over, well, no, let's go ahead and just do that because it'll be fine. Sine of pi is going to be 0. And then in the denominator, we're going to have the limit as x approaches pi of 1 minus cosine of x. And so, I need to make this x up here, y'all. Sorry, make that an x. That'll make a little more sense. So here, if I plug in, I'm going to have 1 minus a negative 1, which is a 2. So notice what we have going on here. We have 0 over 2, and so that's going to give us 0. So that one, they kind of try to be tricky there to get us. All right, so now let's look at number 7. And again, we will be separating these out to see what's going on with them. And so the limit as x approaches infinity of the natural log of x, well, if you think about the graph, natural log of x is going to look something like this. And so as x is approaching infinity, so are our y values, not ever so slowly, but they are approaching infinity. So I know this whole limit then is going toward infinity. The next one, the limit as x approaches infinity of the denominator, the square root of x, kind of in the same boat here. Think about the graph of the square root of x. It's going to be here, and we're heading out towards infinity. So again, in behavior there, we're heading toward infinity. So now we've got a situation for L'Hopital's rule. And with L'Hopital's rule, we do the derivative of the top, derivative of the bottom. Keep in mind this bottom here, we can rewrite that to be x to the 1/2. And so with L'Hopital's rule, we have the limit as x approaches infinity, and the derivative of the natural log of x is 1 over x, over, and here the derivative of x to the 1/2, that's going to be 1/2 x to the negative 1/2. And so this would be a good idea here to try to go through and simplify some of this because, oh my goodness, it looks horrible. So I would just pinpoint this little part and go over to the side here, and let's clear up some of this algebra before we talk about a limit. So this is really 1 over x over, that's 1 over 2x to the 1/2. And so we're dividing fractions, and so easy as pie. We flip the second multiply, so that's going to be 2x to the 1/2 over 1. And so here we're going to cancel, and we've got an x to the 1/2. So it now looks like we've cleared up some of that ugly algebra, and we're going to have the limit as x approaches infinity of 2 over x to the 1/2. And so over to the side, let's think about what's going on here. We've got 2 over the square root of a really, really, really big number. So that's going to tend toward, hopefully we see it's tending toward 0. So the limit here in example 7 should be 0. Okay, so we've got some other forms that we need to look at, and we are analyzing intermediate forms. Notice that when we have a limit where we are multiplying here, then if this is going toward 0 and this is going toward positive or negative infinity, notice our indeterminate form is going to look something like this. And so we've got a problem. We don't know what we can really come up with as far as a value for that. So what we do need to do is try to get this back toward L'Hopital's rule, because if we have our ratio, then we can go through, once we set that up, then we can go through and do our derivatives. So most of the time when you have this product, it's a good idea to rewrite it so that it looks something like this. And that's going to set up our L'Hopital's rule. So let's look at some examples. So here in example 8, notice that we have a value, we're approaching 0 from the right side. And when we start looking at that, we can look at these separately. And the natural log of x graphically, again, looks something like this. And so we've got the case here where if I do substitution and we're approaching from the right side, we're going to have 0 times negative infinity. And that's going to be one of our indeterminate forms. We can't say that that is 0. The limit might turn out to be 0, but we can't say for sure that it is. So what we're going to have to do is try to move this and rearrange it so that we have a fraction. So in our rewriting process, we can say that we have the limit as x approaches 0 from the right, and I'm just going to move that x down to the bottom. But in order to do that, we're going to say that it is x to the negative 1, or we can write it as the limit as x approaches 0 from the right of natural log of x over 1 over x. And now let's see what that's going to yield for us. So let's look at our limits separately again. So I'm going to look at the limit as x approaches 0 from the right of the natural log of x. And notice that if we refer back to our graph, that is tending toward negative infinity. And then over on the other side, if we look at the limit as x is approaching 0 from the positive of 1 over x, now the graph of 1 over x, just a quick review, looks something like this, or it's going to do something like that. So this one, it looks like we are tending toward, if we're approaching 0 from the right, we're heading toward positive infinity. So now we have our L'Hopital's rule. We have a good situation set up here. So we are going to go through and do our derivatives. So we're going to do our L'Hopital's rule. We have our limit as x approaches 0 from the right, and we're going to have the derivative of the natural log of x is 1 over x over, and then if I go through and I do the derivative of 1 over x, remember that again, same thing as x to the negative 1. So that's going to be negative x to the negative 2, or negative 1 over x squared. And so for this one, it kind of looks weird. We're going to have to go over and do some algebra. So over to the side here, I'm going to say 1 over x. That's going to be times negative x squared over 1. Those are going to cancel. And so now I'm looking at the limit as x approaches 0 from the right of negative x, and the graph of negative x, that's just a linear function, isn't it? And with a negative slope, so it's looking something like this. And so now it finally looks like if we're approaching 0 from the right, my limit is going to be 0. Okay, so for our next problem, it looks like here, again, if we go through, we're going to have, let's go ahead and apply what we have. My pen working would help. So it looks like here we're going to have infinity times e to the 1 over really big, or infinity, and then minus 1. So it looks like we're going to end up with infinity times 0. So that's another indeterminate form. We need to try to get this to some kind of ratio. So a good candidate to move would be that one. So let's see. Let's rewrite this to be the limit as x approaches infinity of e to the 1 over x minus 1. And then down here, x to the negative 1, or 1 over x, either way. And so now let's go through and look at our limits separately. We're going to have the limit as x approaches infinity of e to the 1 over x minus 1. That's going to be e to the 1 over big minus 1, that is going to yield 0. And the next one, the limit as x approaches infinity of 1 over x, that again is going to yield 0. So now we're ready. We have our ratio of 0 over 0. So now we can go through and do our L'Hopital's rule. And so if we do that, we've got to look at our derivatives. So we have the limit as x approaches infinity of, and if I do e to the 1 over x, remember that's going to be, I'm going to come over here to the side, that's e to the negative x. Oh, no, oh my gosh, I'm sorry, that's a crack. That's going to be e to the x to the negative 1. Oh my goodness, I can't believe I wrote negative x. Y'all did not see that. All right, so now we're going to do the derivative of that. So derivative of e to the stuff is still going to be e to the stuff. So we're going to say e to the 1 over x times stuff prime. So I need to take the derivative of x to the negative 1. So that's going to be times negative, and then we're going to have x to the negative 2. So, oh my gosh, what a terrible, terrible problem. And then over, and in the denominator, derivative of 1 over x, well, that's going to be negative x to the negative 2. So, hey, those end up canceling each other out. It's a lot better off than we thought. So I'm going to cancel here, going to cancel there. And so I'm left with finding this limit. So let's think about this. It's going to be e to the 1 over really, really big. So that's going to give me e to the 0, which is going to give me 1. So that whole limit was just 1. Oh my goodness. Hey, the next way that we might see an indeterminate form would be right here with infinity minus infinity. So we might have this situation, and so that's going to generate infinity, infinity, so we have this. So it's like, oh my goodness, what are we going to do with that? So right here, we're going to have to rewrite our difference as a quotient or a product. And then after we do that, we're going to have to do L'Hopital's rule or some other thing that we'll do, but it'll be L'Hopital's rule. All right, so what we're going to do here in our next examples is going to be to apply this. So looking at this example 10, again, if we look at this individually, we are going to end up having infinity minus infinity if we go through all of the mess there. And so what we'll end up doing is trying to find a least common denominator, and we're going to add or in this case, subtract our fractions. So quick way to do that, let's do our crisscross. So that's going to be 1 times x, which is x, minus, because that's a minus sign, and then 1 times e to the x minus 1. And then that is all over x times e to the x minus 1. So let's see, please don't try to cancel that. You've just gone in a big O circle if you do. So let's see what we have here. We have x minus e to the x plus 1 over x times e to the x minus x. All right, so we've got a good mess here. Let's go ahead and look at what's going on separately with this. So I'm going to have the limit as x approaches 0 from the right of x minus e to the x plus 1. And that's going to give me 0 minus e to the 0 plus 1. And that looks like that's going to generate 0. And so over on the other side, we have the limit as x approaches 0 from the right, and the denominator x, e to the x minus x, all of that goes to 0. So we have set up a situation where we can do L'Hopital's rule. So on that, let's see what we can do. Again, we're going to make our note here. We're going to say L'Hopital's rule. And now let's look at our derivatives. So we're going to have the limit as x approaches 0 from the right. And when we do our derivatives here, you're going to get 1 minus e to the x over, now be careful right here, that is going to be the product rule. So we're going to have first derivative of the second plus second times derivative of the first, which is going to be 1. And then we have minus x, so that's going to be minus 1. So let's see what we get when we substitute in that old 0. We're going to end up with 1 minus 1 over, let's see, 0 plus 1 minus 1. Oh no, we've ended up with 0 over 0 again. So that means we have to do L'Hopital's rule again. So once more, it's the never-ending limit problem, I do believe. So L'Hopital's rule again. And so for the numerator here, and I'm just going to go straight to the limit as x approaches 0. From the right, that's going to be a negative e to the x in the numerator. And then on the bottom, again, we have our product rule. So we're going to have first derivative of the second plus second times derivative of the first. And then we have plus the derivative here is going to be e to the x. All right, now let's go through and see if we can do our L'Hopital's rule. So, or our limit. So substituting in here, we have negative e to the 0 over 0 plus e to the 0 plus e to the 0. And so that's going to give me negative 1 over a 1 plus 1, which is 2. So that limit looks like we've ended up with negative 1/2.